In this video, I'm going to be going through Chapter 2 Electricity for Year 11 or Preliminary HSC Engineering Studies. And we're going to be going through a fair bit of electrical content here. There's lots and lots of posts that we're going to try and cover in this video. And I will also flick back and forth to, there's like 23 more. So there's a lot of posts. I'm not going to go through everything in a lot of detail. I've already recorded all of the electrical content for both Year 11 and 12. I've covered the whole, the entirety of electricity. But what I'm going to do here is just try and cover this one quickly. So this is going to be my idea is going to be, I won't show the videos as much as well. I'll just click to some key points. And then we can, after I finish recording, the class can watch the rest of the content. Okay, so the first thing is, we look at, okay, well, I will also point out that I've recorded audio way back when. This is for the Year 12s, but still covers the same stuff. The picture is Scranton, Watt, the electric city, and that's because Scranton was, I think, the first city to have electric lights. Paris is the city of lights, but it had gas lights, whereas I believe that Scranton was the first city to have electric lights because it's close to Niagara Falls, which is where one of the first big electric generators was set up. I also have this sad computer from Electric Dreams, which is I think a pretty cool song by Giorgio Moroder and Phil Oakley, who's the singer. So, what are we going to look at first? The first content, I should also point out that Joe Biden was born in Scranton. So, Scranton fact for you. If you play train games, Scranton often gets a shout out. So, Scranton is in 1830, probably the most famous 18XX game. Okay, so now that I've covered those bases, what have we got? Well, the first thing here is we have veritasium and this copper pipe. And what he's going to do, he's going to show this girl in a hat, a copper pipe, and he's got a magnet, and he says, "Is copper magnetic?" And he convinces them all that no, copper is not in fact magnetic. He shows this guy who's got his daughter for the weekend, and he asks them to explain what will happen when he puts just a regular object through, and just ready goes, oh, no, sorry, we've already skipped ahead. The magnet, do you see, it took a long time, it didn't fall quickly. Yeah, maybe you need to see the other one do you see how it's taking a long time to fall? The class does not look impressed, so, maybe I should have shown a skip. Okay, thanks, I got a thumbs up. Girl with the hats, she's excited with it. Anyway, the reason for that is that when you drop a magnet through a copper pipe, what's going to happen, as he explains later, is that it's going to create an electric current. So that kinetic energy is going to transform into electricity, and that's what slows down the magnet. That's why it travels slowly through the pipe. Yeah, because some of that kinetic energy is being transformed into electricity. And then he shows where this is Faraday's lab, and he shows that the same concept is how we generate electricity. So let's leave that for now. There's a concept that we'll talk about very quickly. So there's this thing called the right-hand rule. If you do physics, you might learn about the right-hand rule. I'm not going to go into that in this video. After I've finished recording, I'll talk about Dave Chappelle's joke about what are the 5 fingers. Anyway, but it didn't go over well with the last class. They didn't think it was funny. But there's this thing called the right-hand rule, which is the idea that a current passing through an electrical field will generate a force. If you're interested in going into more detail, go through my other video, which will cover that. My long video will go into that in more detail. The reason why I'm skipping that here is because it's not really something that's going to get tested in engineering. It's something that's going to be tested in physics, to my knowledge. I teach Year 12 students, and I've asked them. I'm pretty sure it gets tested in physics. But it's not really something I need to worry about, and I have a link here if you want to go into more depth, if you want to get ahead of that curve. You can watch a Khan Academy video on that. Okay, the next link I have here is that what I'm trying to get to is, and I have the definition way further down, is movement plus magnets equal electricity. That's what we want to have here, and I'm going to type that in here because I'm disappointed that it wasn't already listed, so I was expecting it to be down sooner. Movement plus magnets equal electricity. Now, there are other ways that you can make electricity, right? Like solar cells don't work on that principle. I don't really teach solar cells. You do it a little bit in year 10 engineering, but that's where photons, if they hit diodes, they produce electricity. They spit out. When photons hit diodes, they spit out electrons. But what we want to learn is movement plus magnets equals electricity, which is exactly what we see in that case. We have a magnet that's moving through, and it's producing electricity in that copper pipe. Now, it's not producing electricity that can be used for anything, but it is producing electricity. So we're going to talk about how we produce electricity down the list. We will talk about solar a little bit, but once we've made the electricity, that's called generation. The next thing we have to worry about is distribution. How do we get the electricity that we make in power plants? How do we get it to the people when they need it? There was an ad way back from like Energy Australia where they talked about how they had like sort of a carton of eggs and they opened it and it was filled with light bulbs. And they said how electricity is made fresh every day, which is a really interesting concept. This is why they try to sell you off-peak electricity at a better rate. Because power plants, they produce electricity 24/7. They're making fresh electricity all the time. And this is why, so last year in 2020, already a bad year, that Texas had a terrible year where their power grid failed. Texas deliberately had their power grid cut off from the rest of the United States because they didn't want to have to follow the regulations, the far more reasonable and protective regulations of the United States. So Texas had an entirely independent electrical grid. And I mean, Texas is the size of Australia, so you know, it's not an unreasonable thing. Anyway, but when the power grid failed in the middle of this unusually cold winter, a whole bunch of people died because they didn't have heat. And the reason, the argument that the oil companies said is, oh, it was because of all of our renewable energy, it can't store electricity. You can't have, so if you have a barrel of oil, a barrel of oil is a way of storing electricity. It's ready to go 24/7. If you need electricity at 2 in the morning, that barrel of oil is ready. Whereas on the other hand, solar power, it's not ready at 2 in the morning because there's no sun. And so this is the challenge of renewables, of wind and solar, is how do you provide what they call baseload energy, which is to make sure that there's always electricity all the time. Because we need electricity even when the sun's not shining, and sometimes there's no wind and we have problems with baseload. Now, the big answer for that is South Australia also had a similar problem with this, and California had a problem with this. So South Australia, they dealt with this by Elon Musk came along and built the world's biggest battery. And that's how they dealt with this problem. And California is looking at how they're going to deal with how they can store their electricity. Usually it's batteries, but sometimes it can be things like you use the electricity, the extra electricity you have, to push water up a hill. And then, when you need electricity, you can let the water come down, and that's how you can get the energy. Or you can do things like melt salt. I've probably gone into more detail on because it's supposed to be a quick video, but moving on. How do we get this electricity that we make fresh every day? How do we get it to people? Well, what do we make? We have wires. We have these big towers, right? These big towers, they carry wires. What do those big towers have on them? Bit of a clue. Can't see the picture of the big tower. It's a bit disappointing. There was a big tower in the thumbnail, and I was really hoping I'd have a big tower. Okay, here we go. So you have these big distribution towers, right? These have huge voltages on them, right? You would not want to climb up these and touch the wires because, I mean, even though they're all shielded, I wouldn't do it. Just put it that way. I wouldn't do it. And these are all insulators, which are probably made out of ceramic. So these wires or these cables, what are they made out of? Some of you, I bet you if it didn't say aluminium on the screen, you would all be thinking copper, right? Yeah, because people are like, copper. Copper's what you use to conduct electricity. This is a Civilization quote. Anyone who plays, I think, Civ 4, that Edison is, we'll make electricity so cheap that only the rich will burn candles. I think I talked about that in the other video, but I think that's pretty true. The rich and hippies. Anyway, Copper. Copper is a pretty good conductor. It's not the best conductor. Later we'll learn about ETP copper, right, which is a grade of copper wiring. So we do use copper wiring, like absolutely. ETP copper is electrolytic tough pitch, and it should be 99.95 or more. Maybe that's OFLC, but anyway, the point is that it has a very high standard. It has to be more than 99% pure copper, but they don't count silver as an impurity. The reason they don't count silver as an impurity is because silver is even better. That makes sense. Yeah, silver is even better than copper in terms of conductivity. Aluminium is only like half as good, right? A little bit better than half as good, but it's way, way lighter. And then it says here that in 1880 in Chicago, the head of a train station noticed that all the outdoor copper wires were deteriorating quickly. And so they substitute, we don't know why they changed to aluminium, but eventually we found that the big advantage is the weight reduction. So we don't really care about the corrosion resistance, I don't think, in modern applications because they're all coated. But the advantage is the weight reduction, because there's a lot of electrical wires and they're all hanging on, well, they're not all hanging on poles. In Australia, they're all hanging on poles. Not all, but a large number of them are hanging on the poles. You don't see telegraph poles when you go to the city, right? And that's because they bury the electrical power in those cases. Okay, so the next thing we're going to look at is electrical symbols. Now, usually what I'll do is in class, and so when I finish this recording, is I'll draw these up on the board. It's not a very high resolution picture, so let's go to Copeland's textbook, and yeah, we're going to have to reload it. There we go. Nice big clear picture. Let's just cover, okay, so yeah, we'll come back to that just because I've already started talking about electrical circuits. Okay, so what we need to do is I usually get people to draw a simple circuit. These days, I mean, what most people are familiar with in year 9 is you draw a circuit with a cell or some sort of power source, a DC power source, a switch and a globe. That's the standard, that's what everyone draws. But these days, you don't really have globes anymore. What you have instead is diodes that emit light, known as LEDs. Now, I will say that you don't always show it with 2 lines. Usually you show it with 2 lines, but I have a book in my cupboard where it instead has the Greek letter lambda. Anyone who's played Half-Life? Half-Life, it has the Greek letter lambda for their symbol. Anyway, Half-Life is what Counter-Strike was based on, and Team Fortress. Anyway, we also have some resistors now, and then finally, okay, we have capacitors, and then we have transistors. So we're going to learn those symbols. The point is that all of these symbols can look different, right? Bit confusing, and you just kind of get used to spotting what they look like. So if we just go back, we can close that window, we can close that window. What do those symbols look like? Well, okay, so what have we got here? What's this thing? I'll give you a clue. R, 4.K, resistor. Okay, and what's this symbol here? Facebook won't make it bigger than that. What's this symbol? What's that? It's still not very clear. It's an omega, or an omega. It's the last letter of the Greek alphabet. What does it represent? Well, it's a measure of resistance, but what is the word that we use to measure resistance? Ohms. We got there eventually. Thanks, guys. Okay. So we also have this thing here. What's this shape? It sort of looks like a table, you know, like a picnic table on its side. What's that thing? Okay, I'm going to draw your attention to the fact that it makes a T shape. T for transistor. It looks a bit like this circle, it's a transistor without the circle. So I will always draw them with circles in an exam because I want to make it easy for you. But it does not have to have the circle on the circuit diagrams. So, okay, let's have a look at this picture. Okay, what have we got here? Well, what's this thing here? A resistor, excellent. Okay, what's this thing here? Transistor, see the picnic table? It's got a T for transistor. Okay, what's this blue thing? Let's go back to our book. A diode. Okay, again, it doesn't have the circle, but it's a diode. I think you always color in the triangle, but, you know, just in case. Okay, what's this one here? It's got two lines coming out of it. An LED. Okay. And what's this thing here? The cell. That's the power source, right? In this case, it'd be a 9-volt battery. Now, it's important to remember that if you need to know which one's positive and which one's negative, the big one is positive because it takes twice the ink to write a plus sign as it does to write a minus sign. So the big one is positive. Some people do draw the small one as a little bit of a thicker line, but that seems to have been you know, less common, or at least in I'm not an electrical engineer, don't listen to me. Okay, so yeah, if you want to show a battery, you can show multiples of those. That means if you want to have like a power source, again, you don't really see that very often. There's also capacitors. I won't go into too much detail, but capacitors do have a definition in the book. So you might want to write out these definitions. A capacitor is a device capable of storing electrical charge. However, unlike a battery, it does not produce the charge and it cannot hold it indefinitely. So I'm sure in the other video I'll go into a little bit more detail, but when I was a kid, a friend of mine, he made a taser out of a capacitor, out of a camera flash. You don't really see camera flashes anymore because everyone has phones. But anyway, yeah, it was an effective device because it built up the charge of that 9-volt battery and left burnt marks. Anyway, if you're interested in that story, check out my other video. So, now we're going to learn about resistors. Resistors, we said, have ohms. You can tell how many ohms are on a resistor by these colorings that they put on there. You don't need to learn that. I just thought just a bit of a resistor shout out. And we saw that resistors can be shown as just a rectangle, or it can be shown as a zigzag line. There is something called a light-dependent resistor, and there's also something called a variable resistor. Okay, so another variable resistor is called a potentiometer, right? So if there's ever a question on potentiometers, I'm going to tell you that I taught you what a potentiometer is. We good? We good? A potentiometer, many of you have done, you've played with Arduinos in engineering or iSTEM in year 9 or 10, and those dials, that dial is a potentiometer. So if that might help you remember that there's activities that involve pots. So then we have diodes. Diodes can look like this. Probably the most famous kind of diode is the light-emitting diode. A couple of years ago, someone got a Nobel Prize for a blue LED. The next thing we're going to do is we're going to watch this video on motors, DC motors specifically. So I'm going to mute it. So, before we watch this motor, what we're going to do is instead watch this one here. Now, those of you who do iSTEM, I believe, not every year, but I believe that your year made these motors in iSTEM. Yep, great. Okay, so the idea is that you take this coil of copper and a magnet and a battery, and it turns. Yeah, so movement plus magnets equals electricity. The reverse is also true. Magnets plus electricity equals movement. Yeah, magnet, that's the circle. Electricity, the battery, equals movement. Now, the thing is that we're going to watch in a little more detail. Okay, how does that work? Well, they say, let's take our simplest possible example, this one here, right? And we've got a magnetic field, right? and we've got a current. And what I say happens if you have a magnetic field and current? You're going to get a force, yeah, because it's the right-hand rule. Now, again, I haven't explained that yet because, I'm going to pause that, and if people want more detail, at this point, you're just going to have to accept that's the case, but we're going to go through it a little bit after I finish recording. Now, what's going to happen, though, is it's going to get to this point, and then, right, at this point, it just wants to get stuck there, because now it's like, oh yeah, I've achieved what I wanted to do as a magnet. So that's why they put a split in the ring, so that way the current reverses halfway to keep the flow of electricity. Yeah. Again, this is probably getting beyond the level of engineering and now starting to head into physics territory. So if you're not doing physics, you could just ignore that. You could just say movement plus magnets equal electricity. Okay. Now, what you find is you get a bit of a wave pattern. You get like a peak and then a trough of energy. If you want to have consistent power, then what you can have is an extra coil of wire. And then obviously, now you're going to have a smooth flow. And then the next variation of that is you can then just have stacks of them. And this is what we actually have. And that's called an armature. An armature is when you have lots and lots of wires of coiled. And then you put some magnets in between them, and that makes it even better. Yeah. Okay, so this goes on to then show, okay, so you can see how we went from that simple coil now up to a modern connection. Now, we can wire these in series or in parallel, and if we wire them in parallel, we call that a shunt motor, and we can also have a series motor. Okay, so series, no surprises there, right? Series, shunt, parallel. Okay, series motors, so there's this TV show, not really, but called DC Motors. It starts really strong. It's a really great the first few episodes are really good, but then as it starts getting on to, season 2 and 3, it's terrible. No one watches it anymore. It really died off, right? That's series motors. Shunt motors, on the other hand, start slow, but they've really, really good high speeds, right? So what we can have there is shunt motors. You can see that they have good high speeds, and then you can actually combine them if you want. You can have a combination that has both. There's then a concept called EMF, back EMF. Now, to explain what back EMF is, now I'm going to go back to the start of the book. Okay, we need to know some basic principles. Hopefully, you guys have done like Year 9 science, and in Year 9 science, presumably you've learned about Ohm's law. Put your hand up if you've heard of Ohm's law. Even if you don't know what it is. Great, okay. So, what we should be familiar with is a couple of terminologies. In the other video, I actually show, the guy who came up with voltage, Count Volta, and I show a picture of ohms, and I explain why current is the letter I, but we don't care about any of that. We're just going to get to the nuts and bolts of it. So current, some people remember CIA. Current is represented by the letter I and is measured in amperes, or in this subject we're just allowed to write amps. And amps is one of the base 7 SI units, even though I said we only learned 3, and then I just slide in Kelvin, and I did watch the 360 degrees of heat yesterday. And amperes is another one. I think they're really the only 5 we use. We don't really talk about moles or the measure of light intensity in this subject. Okay, so current is the flow of electrons or charged particles, right? Current is the flow of charged particles. If you wrote current is the flow of electrons, I'm going to accept that. The thing is, you can conduct electricity with ions, and this is why salt water conducts electricity. But again, that's not really something we're going to talk about in the subject, so that's why I'm saying it really quietly. Okay, but current is the flow of electrons. But a bit of a crazy thing that I'm going to show when we talk on a board. Hold on. Okay, so there's an XKCD where this electrical engineer develops a time machine, and the first thing he does, he goes on an urgent mission. He goes to Ben Franklin and tells him that the circuit diagrams are wrong, right? So when we draw those diagrams, remember we said which one is the positive, the big one or the little one? the big one, because it uses twice as much ink. Electrical engineers, they like to pretend that current flows from the positive to the negative. But we know electrons are negatively charged, so in actual fact, the electrons are flowing from the negative pole to the positive pole. So how we explain this in things like the Manga Guide to Electricity, which I will have posted an excerpt, because anything more and I might get, copyright strike. In this thing here, they describe current as being opposite the flow of electrons, and that's just what we have to that's how we have to try, and that's how electrical engineers go to sleep at night, is that I'm just going to tell myself that current is the opposite of the flow of electrons. Yeah, that's just what we're going to convince ourselves. Yeah. Electronics and circuits. I don't have this one. Anyway. So, and with all XKCDs, it's really difficult for me to go back with the way that I'm just going to have to move my screen, which is a shame. What I can do is they explain all the jokes. Yeah. God, the internet's great. They explain all the jokes. So if you don't get the jokes, like, the android's dream of electric sheep one, where he starts counting they go to negative, like Gandhi. Anyway, you don't need to worry about that. What is this rambling of this man? Anyway, the point is they explain the jokes, because some of the jokes can be a bit, nerdy. And they might be a nerdy that you're not that particular kind of nerd. So this is a way to, improve your, the areas that you can be a strong nerd in. Okay, so we talked about current. Current goes from the positive to the negative. It's opposite the flow of electrons. But we could write, if you had a question that said, describe current, you said the flow of electrons, I would mark that as correct, even though current is a force that travels opposite the direction of the flow of charged particles, such as electrons or ions. And I'm not even, I'm just happy with current is the flow of electrons. We all good with that? We can move on. It's measured in amps. Okay, the next thing we have is this thing, potential difference, or E. Why would potential difference be E? It's like, do we not have enough E's already? Because you guys have already seen stress and strain, and you've seen there's a lot of E's in stress and strain, right? There's too many E's already. Why would they choose E for potential difference? And then it's measured in V. Well, you, I'm sure, are all familiar with, how long has that been there? With this concept of voltage. Have you heard of volts? Yeah? Well, like, Eminem, or Marshall Mathers, who sometimes goes by the name Shady, right? The real Slim Shady. All the other Shadys are just imitaties, right? It's like, anyway. These days, the name that the artist formerly known as Voltage goes by is electromotive force. I stress that because when people say EMF, they think electromagnetic field, and that's what I thought for like 4 years of teaching this subject, I mean, maybe not, but, the point is I was regularly getting this wrong. That's why I say electromotive force, to help people remember that it's different to the electromagnetic force. What this is the potential difference between two charges. The idea that there's a whole lot of positive charge on the positive terminal, and there's a whole lot of negative charge on the negative terminal, and the difference between those two charges can be measured in voltage, in volts. Right? That's the potential difference between those two. And that is going to be the pushing force that moves those electrons around. The bigger the difference in those charges, the more force that is going to push those electrons through the circuit. We good? Okay. Lastly, we have resistance. Resistance is how difficult it is, or, it's, what is it? The problem is it's hard to say resistance without saying the word resistance, right? It's the resistance to the flow of electrons. But you could say it's a measure of how difficult it is for electrons to flow through a circuit. Yep. Okay. So now that we've covered those concepts, we can now talk about back EMF. So what's back EMF? What does EMF stand for? Electromotive force. And what's it measured in? Volts. So we could just say it's reverse voltage. Yeah? That makes sense. Reverse voltage. How do we get reverse voltage? Well, what happens is it's almost revolting. No, it's not. Don't worry. That was silly. Shouldn't have gone there. Okay. So the idea is that back EMF is that when you have movement plus magnets, it equals electricity. Well, I have a moving magnet. And yes, I know that I'm saying electricity plus movement equals, electricity plus magnets equals movement. In this case, DC motors, they actually produce an amount of voltage backwards, right? Which reduces the total net voltage on your circuit, right? So that's something you need to be aware of. Now, I have eaten 2 hats in the last 2 years, right? The first of those hats I ate because I said that there was not a question on, I had not seen a HSC question on EMF, which really was a pretty silly thing to put a hat on when I had a student in class who just got onto Google and searched the word EMF and was able to find it, and I had to eat a paper hat. Tell you what, a lot less tasty than I anticipated. So now I try to be a little bit more hesitant in my my throwing out the eating of hats. But back EMF, I will say that although I ate the hats, that the question hadn't been in the modern HSC. So this HSC was revised in 2011, and this question was from 2010, which was from the old syllabus. But you know, it's probably still a question that could be asked of you. Now, what we have here is we have this spinning coil. How do we stop this coil from just sticking at the bottom? Why doesn't the magnet just stop it at when it gets to the bottom? When like, you know how we kind of create an electromagnet in this coil, and the electromagnet is drawn or repelled, right? It is drawn and repelled by the magnet. This doesn't have a split ring commutator in it, so how is it going to stop that the magnet from slowing down and eventually, you know, being attracted by the magnet? No. So you guys might remember that when you make these, there's actually a very thin plastic coating around the coil, and you would have sanded off half of the copper wire. This is not a question that's going to be in the HSC. Don't worry. Moving on. Okay. Lisa, in this house we obey the law of thermodynamics, because you see some idiot videos where lots of people like to prove that they've created free electricity. So it's not really a thing. Okay, so then we have to learn about 3-phase AC motors, and AC motors. I think objectively there's a good argument to say that AC motors are better, especially if you have 3-phase electricity. AC motors are really fantastic, but I'm not going to go through that. You're going to watch that video because it explains it way better than I can. So let's have a look. Okay, now we're on to electrical safety. Okay. So I'm going to skip in this video. I'm going to skip over a couple of concepts. So I'm going to come back to electrical safety because I have a whole YouTube post on electrical safety. In terms of fundamentals of AC and DC, that I will talk about because I've got that. I can see it right here. So there's this guy called Electroboom, and he has a video where he talks about the war of the currents. Actually, I didn't have it here. He's just talking about AC motors. So we'll have to come back to that one later when I've got it set up. So DC motors just have a continual flow of electricity in one direction. Yeah? Like Harry Styles and his mates. Yeah? Get out, get out. Yeah, anyway. Okay. And then AC, what happens is it goes around in both directions. Now, a way you could imagine this is imagine we all got up as a class and we started doing the conga. Conga, conga, conga. I'll put on a Pride and Prejudice video about the conga later. Anyway, I'm currently transcribing Pride and Prejudice into shorthand. Just a bit of a fact for people. Anyway, oh, maybe I'm going to have to edit that out. No, we're just going to ride the lightning on that one. Okay, there's very little chance it's going to blow up in my face. Okay, so with DC, the conga line just keeps going in the same direction, right? The conga line just keeps going clockwise the whole time. Whereas with AC, they do conga, 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 turn around, conga, 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 turn around, conga, 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 turn around. And in that way, the electrons, they never really move far from where they started. They just, again, it can be other charged particles, but for engineering, we're always going to say electrons. The electrons are going to move a little bit left, and then they're going to move a little bit right. And you might think, well, how do you make a motor work without that? Well, you still can make a motor work without that because there's still movement, and the movement is enough to create that motion. I do have something on AC versus DC. I just don't know where it is. I'm disappointed that I can't see it. I'm going to pause. And we're back. Okay, so Electro Boom, yeah, he makes some pretty good videos that are good for electrical engineers. And he says, okay, so there's AC. I've already said that AC is dangerous. And so Tesla was the fan of AC, and Edison was DC. He's like, why am I so angry? Right? Anyway, yeah, why am I so angry? This is where, anyway, then he goes and, like, you know, zaps himself, and, you know, he's a big fan of physical comedy, that dude. Okay, so alternating currents. I'm looking for a GIF. Here we go. Found it, don't worry. So this GIF here, it kind of gives you an idea of what AC looks like. So using water as an analogy, see the water's going left, then it's going right, left, well, whatever, your relative. That's kind of the idea, that there's still movement, and the movement's enough to make your light illuminate or whatever. It's also worth pointing out, before I move on too much further, that electricity was first used to light up the city of Scranton. That was really what where Edison started, was that he would make electricity so cheap that only the rich would burn candles. But eventually they wanted to start applying, so we can use electricity for heat, right? So you might see like those, I can't, you know how you have stoves that look like that? Yep. Electric stoves, so that they realized they could, you know, you could make electricity heat things up, and then they got to electric motors. And then obviously, you know, now we have the modern economy is built on computers, which all run on the electricity. I often think about what a fantastic deal electricity is, that if I had to put a $2 coin every day in my house just to use electricity, I would happily pay that $2 coin, because electricity is just the bee's knees. Okay, so how does alternating current work? Here he talks about why we use three-phase energy, why that's an advantage. Here's how we make three-phase electricity with these things called rectifiers. How do we use rectifiers? Well, we use diodes to make rectifiers, and rectifiers rectify or convert AC to DC. We're going to learn more about that. I've just covered that recently with Year 12s, and I have a picture of Wreck-It Ralph and the band AC/DC and Edison and Tesla. It's all happening in that cover photo. There's a movie called War of the Currents. It has the kid from About a Boy, who then went on to be Beast in the X-Men movies. He plays Tesla, and it has Cumberbatch, who plays Edison, I'm pretty sure. War of the Currents. I think I showed that in the other video. Here's like a poster that's, you know, like the War of the Currents, but I bet you this picture's going to be bad. There we go. I'm not going to pay for a high resolution picture of that. I'm sure I got it somewhere else. Okay, so before I moved on, I said I would go back and say, hey, you know that movement plus magnets equal movements plus magnets equals electricity. Electricity plus magnets equals movement. Well, here is the definition that I'm going to get you to write in your textbooks, so that way you know what to write when I have a question that says, describe how a simple DC motor works. Yeah, that's what you're going to do for homework. So I'm going to write that up in a second. And that's where the answer for that is going to be. Let's go back to this post, and what we have after that, okay, we have AC motors, is we have how do we make electricity? Where does electricity come from? Well, where electricity comes from is we need movement to go with the magnets to make electricity. Yeah, typically, now solar is different. Remember we said solar was different? Yeah, but there's lots of other ways we can move those magnets. How do we move those magnets? We don't move the magnets. We technically move the coil, but you know, how do we move things? I'll tell you what we call it. We call it a generator. How do we turn the generator? Fuel is a way of doing it. Okay, how do you take oil and then turn that into movement? You burn it, and then what do you do with the heat? So this is great. We're going to learn something. So what happens is you burn the fuel. The fuel is then boils water. The water makes steam, and then steam turns the turbine. Yeah, I did this with my daughter when she was very little. That we got a pinwheel, and I have a saucepan that has little holes on the lid. I don't know if you've got those as well. Anyway, so it means steam comes out of that little hole in the lid, and we made it turn a pinwheel. And so, well, that's how we make electricity. I don't know if she'd remember that, but there's lots of ways we can boil that water, right? We can burn oil, or we can burn natural gas, or we can burn coal. Right, that's the one that ScoMo likes, coal. Right, no one else in the world likes coal. Right, I say the rest of the world will probably stop burning coal probably within 10 years, and that's a bit of a worry if coal is like your third biggest export. Right, you know, it's not a great place to be where that's one of your biggest parts of your economy, and you have a prime minister who's like just holding on for dear life. Anyway, I'm gonna leave it there. Anyway, moving on. Another way that you can do it is you can use a nuclear reaction, because they make heat. You can use that to boil the water. And that's how nuclear generators work. Australia doesn't have any nuclear generators. We have a nuclear power plant. Sorry, we don't have a nuclear power plant. We do have a nuclear reactor, but we don't have a nuclear power plant, right? We use our nuclear reactor to make medicine and stuff, and to do science. Whereas you need a much bigger one to make electricity. France used to make almost all of their electricity from nuclear power. Japan used to make all of their power from nuclear power. Since Fukushima, that is now a lot less popular. Japan, if anyone watches the excellent German TV series Dark, it's all about them shutting down a nuclear reactor. Okay, then I have a whole bunch of posts about people talking about different ways of making electricity. So this guy is talking about nuclear waste. There are some swears, be warned, right? You have been warned that if your parents would not like you to see swears. Okay, then I have what's interesting is places like Reddit are great for if you're like, you know, a nuclear industry and you want to just pay someone a couple of bucks and it doesn't cost you a whole lot of money. You can just pay someone, a nuclear engineer, just to sit on Reddit all the time. And anytime anyone says Fukushima was bad, someone goes on and says, no, it wasn't. Right? And that's just what they do all day, every day. It's like, Fukushima, no, it was a small price to pay, and then they just give you all the facts. Now, I have been won over probably by these astroturfing is what they call that. You can look it up. AstroTurf. I've probably been convinced that thorium is the future, and that thorium is probably the answer to climate change. But that's well beyond the scope of this course. You don't need to know about thorium. But yeah, I've probably been convinced. When I used to be an engineer, I went to a conference and they talked about nuclear power. And this is how I got started on a conversation with one of these people on Reddit. Is I said, there's just not enough uranium. Right, there just is not enough uranium for everyone to use uranium, for everyone to start using nuclear power. And then he started saying, well, thorium is, the future. And at the time I went to that conference where I saw a leading expert in Australia talking about nuclear power, thorium was a long way away, whereas 10 years on, thorium is a lot closer, but still kind of a long way away. Whereas solar is here and it's here right now, wind is here and it's here right now, thorium is probably still the future. Okay. So here I have Trump talking about windmills. You can watch Trump say it himself, but yeah, he knows more about windmills than anybody. And he knows that they're mostly made in China and Germany, and that they do tremendous harm to the environment. They're spewing poisonous gases into the atmosphere. And if you want to see some dead birds, you should go to a wind turbine because it kills all the birds. And then the White House had to say that they could not explain Trump's comments because just insane. Anyway, luckily, you don't have to listen to it anymore because he's been kicked off all the social media. Okay, wind is outpacing pretty much all other sources of electricity these days. You pretty much have to be insane to build a coal power plant or a gas power plant. Australia, still looking at building coal and gas power plants. No one else in the world is doing that now because they cost more money. Scotland now has run, it has a period of times where it runs entirely on wind, but Scotland is a big empty country. With lots of wind. Okay, fusion is always 50 years away. What they call fusion never. The idea is that funding for fusion is always 50 years away. This is how quickly we could get to fusion if we put heaps of money in, and this is how long it would take to get to fusion if we put in a little bit of money. And then this is what they call, the red line is fusion never, which means that you never have enough money to actually get to fusion. And then this is the actual funding for fusion. So yeah, people like to talk about fusion and how it's just around the corner. Fusion never. Okay, reality check on renewables. This is some guy talking in a TED talk and saying how England would really struggle to run its country just on wind and solar, right? Just because of the efficiency of wind and solar. Even if they were perfectly efficient, there's just more people than there is land to generate. But you know what? A lot of countries, they have their wind farms in the ocean. Okay, and that's where we're going to be for. So from here, what we're going to talk about is we're going to cover Ohm's law a little bit, and then we're going to go into electrical safety. So we have this picture here, which is a bit confusing, but at least it uses V for voltage, which for me is the way that I like to think about it. But we're going to look later and see that the HSC doesn't use V for voltage. They write E equals IR, right? So we just got to know that V, right? V could be voltage, E for electromotive force could be potential difference, right? It's just like shady. There's different versions. Okay, so this is the formula. There's lots of different ways, and this kind of covers everything, right? So what we're looking at is V equals IR. Ohm's law, I think, is actually I equals V over R. That's what actually Ohm's, maybe, I think I equals V over R, I think is actual Ohm's law. The point is, everyone remembers is V equals IR. A good way of doing it is using these triangles. It seems that everyone in this class is familiar with these triangles, that if you put your finger on the V, V equals I times R. If you put the finger on I, you get V divided by R. So that kind of gives you that. Also, we have this concept here that we have, we've looked at, because we looked ahead, we did look a little bit at other SI units. So we looked at work, 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 work. Now, I said that song, to help me remember that song, I remember F in S, right? F and S, right? FS is the formula for work, 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 work. Force times, and what is S? Force times displacement is work, work, work. And what units does Drake like? Joules. He does not like calories. Yeah? So he, like the Drake mean, I'm not going to click back on that because it's the short version of the video, but you've seen that already. Okay, so we also in this subject need to know power. Can anyone tell me what is the unit for power?
See, I have a first baseman. I know you got a first baseman. I asked you what's the first baseman's name?
No, what's the second baseman?
I'm going to stop asking you. I asked you what's the first baseman's name?
What's the second baseman?
I don't even get past the first. All right, who's on second?
Okay, so what's the unit for power? Yeah, no, not a question. Get it? What's the unit for power? Yeah? That groan of dad jokes. Okay, great. What's the unit for power? Okay, so here's the stuff that we're going to focus on, right? This is all the stuff that relates to electricity and electronics in the HSA. Let's get a cleaner version because, you know, that one's a bit not so great. Here we have power up here. Power is the unit. What's the unit for power? Yeah, I know, I just said. Anyway, what's the unit for power? So power equals work over time. And then we're going to learn, like, there's some more advanced versions. But for the moment, what's the unit for power? Okay, what we have here is E equals IR. What's E equals IR mean? V equals IR. So voltage is equal to amps divided by ohms. Yeah, is a way of thinking about it. Volts equals... Wait, did I say divided? Great. I had that look of a student who's like, I've said the wrong thing, which is great because no one wants to be wrong on the internet. Voltage equals amps times ohms. Thank you very much. I was literally looking at it and I just got excited, I guess. Okay, then I've also got power equals amps squared times ohms. Let's go back to here. We can see power equals power, which is, what's the unit for power? Yeah, I know, I just said. Anyway, power equals, it says current squared times resistance, or you can write it as P equals IV, or even better, you can write P equals IE, right? And then it's pi. And people like pie. I don't know. I like some pie. I'm very picky on my pies, but I do like some pies. There are pies that I'm a fan of. Okay. Now, I have already recorded all of the electronic stuff. So I have covered this stuff here about calculating resistance of parallel circuits. And I have done quite a lot of stuff on digital electronics with gates. To get to very quickly, where do gates come... Sorry, I just bumped the microphone. What are gates? Well, the very short version, gates are circuits that are made up of transistors, right? Transistors, right? We haven't covered this yet, but it's homework on the board. Transistors can be used for switches or amplifiers, and diodes allow electricity to flow in one direction. I'm just saying that because it's homework on the board. What we're going to go to first is we're going to go to electrical safety. I say that's homework. Let's see. It does say here, does it say diode? It does. And does it say transistor? It does. So there you go. I don't feel bad about covering that a little bit early. Okay. Electrical safety, what we're going to look at here is we're going to look at earthing, we're going to look at circuit breakers, we're going to look at fuses, we're going to look at safety switches, better known as RCDs, residual current devices. That means that if I have a question that says residual current device in an exam, I'm going to say I've taught you what that is, even though I've only written it down as an abbreviation. Maybe I could write a question on the board that says, describe RCDs, or describe the role of RCDs. Describe role RCD. There you go. That way you need to know what a residual current device is. Double insulation, shielding, and compressed air. So I've got a fair bit to cover. This is where I cover all of my stuff on electrical safety. So first of all, when you cut open a power plug, right, you're going to see some different colored cables. Well, you're going to see different colored wires in an electrical cable is the terminology they use from when I was, when I did a work experience with an electrician. Okay, this picture is not the highest resolution, which is, I apologize for. In Australia, we use... Well, okay, so most of the world, the European Union, South Africa, right, they use brown for power, right? That the active, or what they call the phase, the active is brown, the neutral or the return is blue, and the earth is green and yellow stripes, right? Now, when I was in high school, Australia used red, black, and green, but they've now adopted the same one that is used by Argentina, South Africa, and the European Union, right? So they've now adopted this standard. Probably because of color blindness would be, I think, the reason, but I don't know. I'm not an expert on that. Here we can see this is what they should look like when you cut them open. We got, what do we say? Brown is the phase, right? So the thing is you can have multiple phases. There could be 3 phases, right? In which case you'd have more than one, which is why the US doesn't use the same convention. Blue is the neutral or return, and then green and yellow is the earth. Okay, where does the earth go? Well, the earth is... Electrical safety is basically that... let's start with lightning, right? So in a storm, what you can have is a whole bunch of water bashes against each other in such a way that it starts to build up a static electrical charge. Keep in mind, I'm not an expert on this, so I could be saying a few things that are wrong, and I'm sorry if I'm saying something wrong on the internet. Anyway, it builds up a big electrical charge, right? It builds up a big collection of, free electrons, right? And then, eventually, the ground has effectively a positive charge in that it can take a lot of electrons, right? And eventually, that starts to look so attractive to all those electrons in the air that they jump from the clouds to the ground, right? In what we call lightning. If we do that same principle but with a welder, we call it an electrical arc. Yeah, we build up electrons at one end and they want to go to the other end and they jump through an electrical arc. Same concept, right? Now, the thing is that ordinarily electricity flows from the brown to the blue. Yeah, it flows from the brown to the blue. But it's a long way between your toaster and where the electrons have come from, right? The power plant. Those electrons have come from a power plant, well, I mean, AC, it's not really exactly the case, but let's just say for the sake of argument, right? They've come from the power plant, they've gone to your toaster, and they've gone back home. Keep in mind, they're just doing the conga, 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 change direction, conga, conga. But for the sake of the argument, we're going to stick with this idea, right? Now, if you decide to stick a fork in the toaster to get your toast out, suddenly the electron has another option. It says, hey, you know how we could go all the way back to the power plant? Instead, why don't we just go to the ground? The ground, there's heaps of place for the ground, right? So there's heaps of electrons. They love electrons in the ground. Let's go to the ground, right? And the ground is way closer. When I say the ground, I mean like literally the earth, right? Like the physical dirt, right? Shh. The dirt is a lot closer than the power plant. And all it needs to do, it's like, yeah, but if we go that way, we have to go through Billy. You know, we have to, and like Billy, he doesn't conduct as good as the copper or aluminium that it's actually in the distribution network. And it's like, yeah, I know that Billy's not as conductive, but it's a lot closer. And it's like, okay, you've convinced me. Let's go through Billy. And then it runs through Billy. Now, that may or may not end well for Billy. So instead, what we do is we have another wire that's connected to usually like a pipe or something that's plugged into the ground of your house. So that way, instead of running, like now there's 3 choices for the electrons. We could go back to the power plant. That's a long way. We can go to the ground, but if we're going to go through the ground, that's okay. Are we going to go through Billy or are we going to go through this copper wire? It's like, well, the copper wire is like way, way closer. It's like, yeah, okay, let's go through the copper wire. And that's good for Billy. Yeah, Billy is happy with this scenario. No, okay, because only in certain circumstances is there going to be a leakage where the electricity has that option. Sometimes it doesn't have the option of going through the earth, right? So it's not always going to work. It's one safety, right? But just the same as like family planning, it's good to have multiple forms of what they call dual modes of failure, right? Sometimes you want to have more than one backup. You know, if you're in a spaceship, you probably want to have a secondary backup because, you know, it's a long way home. Of being in a spaceship? I don't know. I'm not an electrician. I'm not an electrical engineer. I'm a guy who can tell you enough to pass the exam. Okay. Now, in this video, there is a distinction between earthing and grounding, right? I do not care about this distinction personally, but I can now say that I have taught you there's a distinction between earthing and grounding. Yeah? Done. Okay. Now, if you look around you and you look at the computers in place, you can see there's a whole bunch of tags that are connected to power cables. That means that someone once a year comes and checks in any workplace. They have to check that the electrical appliances are in reasonable condition. Now, I've done this course, right? I don't know why I thought this was a good idea to do this course, but I did this course. It was a one-day at TAFE. Where you get a machine and, you know, you touch it on the machine, you have a look at the cable. It's pretty simple. But that's a way that we ensure safety, is to make sure that, well, we're going to talk about double insulation. Do we talk about double insulation? I don't see it here, so I think probably need to talk about. This is probably where I want to say not everything has, toasters do, but not everything has 3 plugs. It's actually pins. 3 pins are earthed. If you look at the plug with they have to be double insulated, which means that there can't be any metal surfaces. Yeah, so that's what I learned when I did this course. If something has an outside metal surface, it's not double insulated, right? So the idea is that everything is, there's no metal parts that you can touch. And you learn that at the test and tag course. There's also something called shielding. And the idea is that, like, in this case here, we have 400 kilovolt cables, right? 400 kilovolts is a lot. Trains, the cables that run on along the train line, they're 33,000 volts, 33 kV. And then the train itself runs on, I believe, 1,050 volts, right? I'm pretty sure. DC train voltage. What about this? Is something I used to know off the back of my head. Yeah, okay. Yeah, 1500 DC volt. Okay, I got the zero in the wrong spot. Okay, so the idea here is all of the phases, they're in the center, and then you have a big insulator, and then you have the neutral on the outside. So that way, if you cut into this wire, you don't just instantly die, because instead all of the active electricity is in the middle, right, and all of the return is on the outside, so that you have to cut through the entire cable in order to electrocute yourself, right? If you cut through just part of the cable, if you only just cut through that part, you'll be okay. Yep. I have no idea. Yeah, it's 40,000 kilovolts. Sorry, it's 40 kilovolts. I have no idea. Okay, so here we have RCDs and circuit breakers. They are not the same. Not the same. Okay, residual current devices operate by measuring the current balance between two conductors using a current transformer. Okay, what I would say is there's a device that can tell how much current's going into the house, and it compares that to the current going out of the house. So you turn the toaster on, suddenly it starts drawing more current goes into the house. It says, oh yeah, there's this many amps going into the house. And then it looks and checks, okay, there's 100 amps going into the house, but only 10 amps coming out. Uh-oh, where's those 90 amps going? Through Billy, right? So it sees, in a millisecond, it sees that the current is going not through the house, but through Billy, and it shuts it down, right? There's a hand gesture. If you watch it, you go, shut it down, right? It shuts down the current. That's how RCDs work. Sorry, people listening on the microphone, I apologize. Okay. Now, there is also circuit breakers. We don't use earth leakage circuit breakers anymore. They've been replaced with RCDs. There's also circuit breakers. What did we used to use before we used circuit breakers? Fuses, exactly right. Do we still use fuses? Where? Excellent. Cars use fuses. These are the kind of fuses you buy for cars. They're color-coded. Yeah, so you can tell, what they're rated to. Where do we use these? I used to, when I was a kid, I used to play with these. My Lego men used to carry them around like they were like the mutagen from Ninja Turtles. Ninja Turtles, pretty important role in my life. Okay, what do you use them for? Yeah, okay, yeah. So, household appliances and things like maybe a stove. Right? Maybe a stove. The thing is, though, these days stoves usually have their own fuse. Yeah? Okay. This here is what fuses... Well, I mean, some of you might have houses. I was at a friend's house and I looked at their fuse box and it still looks like this. Right? You have an insulator and you have a small thin piece of wire. Right? And that acts as your fuse. Right? The idea is that instead of setting the house on fire, sometimes, like, let's just say that you have an electrical spike, right? Electrical spikes happen, especially during storms, or you might have too many things switched on in your house. You have an electrical spike. What happens is the fuse just melts, right? The fuse melts before the house catches on fire. It's a great safety precaution. But a couple of problems. One, in the middle of the night, you have to get the torch. Right? You go out in the middle of the night, you get the torch, you're holding the torch in your mouth while you're wiring up the fuse wire to replace the fuse that just blew. And then it blows again 10 seconds later and you're out there doing it again. Now, instead, they have these handy-dandy fuse boxes where all you need to do is just click the fuse. It's great. It's a huge innovation, a huge improvement in our quality of life. How do they work? Well, They have a bimetal switch. Or no, they used to have bimetal switches. These days, I think they're more. They usually have small computers. But I have some videos. So this video here, he talks about how to. Look at that video. How excited he is.
Don't worry.
Don't worry.
It's a fuse box. You cannot get electrocuted. If a switch.
So what it's saying is, if there's a problem, you just find the one that's wrong.
Or make sure the RCD switch is on. 9 times out of 10, it's the RCD. Don't worry.
So if it's switched in the off position, you just flick it back on. That's it. That's all you need to do. I'm just trying to find the picture. So here we can see this one here is tripped.
Yours might be higher up on the wall. If it is.
Yours might be higher. Okay, so here we go. This one here is tripped. And you just flick it back. Now, sometimes that'll happen and it'll just instantaneously flick back off. And that's because, like, for instance, we had a slow cooker that it was the device in our house that was tripping for some reason. And we were going to chuck it out, and in the end we just gave it another crack. And, you know, it's a bit of a risk when we leave our house and that, you know, maybe the slow cooker's moving on. Anyway, what have we got here? So we now know the difference between fuses and circuit breakers and RCDs. We don't need to really worry about leakage current. Okay, now there's something called the hierarchy of control, right? So the hierarchy of control is that if possible, the best thing we should do is we should eliminate a risk. And if we can't eliminate the risk, then the next thing we should do is we should try to substitute it for something else, right? And if we can't eliminate that, then what we should do is we should have a physical barrier. And if we can't put in a physical barrier, we should have rules. And if we can't have a rule, then we have the last layer of protection should be personal protective equipment, PPE. I remember I was sitting on a panel for a job interview, and my boss, the director, he was explaining this concept to. He wanted the interviewees to be able to explain the hierarchy of control to them, and he used the 5 things. And anyway, the analogy that he used at the end of the interviews when he explained it to the candidates is if you were cooking something, if you wanted to bake a cake, well, first of all, you could say, hey, have you ever thought about not making a cake? Right? Just don't make a cake. Right? There would be no risk of burning yourself if you just didn't make a cake. And you're like, yeah, but I want a cake. And you're like, okay, fine. So elimination's not an option. What about substitution? How about instead of a cake, what if you made like chocolate mousse? What if you just had ice cream? Could you have ice cream? How about an ice cream? Right? Maybe you could make it in something that you could microwave. Right? My wife, she makes a carrot cake that you microwave. How about that? And you're like, no, I want a cake. I want a cake that I bake in the oven because I like, you know, regular just chocolate cake. And then you say, okay, fine. What we could do is we could put a barrier up so that way the baby can't walk over and touch the oven. You're like, okay, that's fine, but I need to be able to touch the oven. And say, okay, that's fine, it's fine. So we'll have a rule. We'll have a rule that you only touch the oven when it's safe to do so. And you're like, okay, but, you know, I kind of need to get the cake out of the oven when it's hot. And you're like, okay, fine. So what we're going to do is we're going to have the baby barrier, right? We're going to have the wall to stop the baby from touching the oven. And we're going to have a rule that you're going to avoid touching the oven if you can. But at the times when you do have to touch the oven, you're going to wear an oven mitt. And that's your PPE. And he's like, okay, fine. So there you go. I've just taught you about the hierarchy of control, right? Now, there are standards controlling electrical safety. If you want to make a toy or anything that plugs into a wall, you need to comply with AS 3820, right? And that specifies what the plug needs to look like, all of these sorts of things. If you want to do electrical work, you need to comply with AS 3000. And then I have a terrible joke that you can look at later.